All righty, let's see. I think I got this thing up and running properly. Let me get a full screen. Come on, where are you? All right, full screen right there. That should work. It's not. Let's try that one. That's better. All right, hopefully you're seeing things properly. It's Tuesday afternoon. I've just put a whole bunch of things on the board. So I'll probably be telling you tomorrow, I can't make Thursday's class. Getting the car work done, the brakes aren't working. Right now, I've had to take the floorboards out and I'm doing the Freddie Flintstone. Get back and forth. No, it's not that bad. But I got another brake that has to get fixed and that's me. So I might miss, looks like something's on the camera here. I might miss Friday's class as well. So you're going to do some group work. And what I'm going to do is lay out all the new material that I'm hoping we cover. About 20% more problems, about 15 more problems. And you've been doing 60 on tests at this point. And the goal of this whole process is to have a foundation at the end of the semester. So you're still going to be working on all those problems that you didn't get on the last test. You'll be working on those every test. And I'll be tucking in the new problems for you to get familiar with. And we have until like around December 15th to have everybody get every single problem right. And because you've been doing it so much, the goal is that you take it into your next class, because if you can't, that means you didn't really learn it. And that's one of the problems facing, I think, mathematical instruction in the country right now is people aren't remembering what they did in the previous level of study for the most part, because you learn it for a test, memorize it, memorize the patterns. This goes here, that goes there, but you don't have enough time to actually conceptualize what's going on to really understand it. And that's what we're trying to do. We're trying to get a conceptual understanding of the problems in front of us and the fundamental problems that you have to be able to work with in order to get to the next level. Now, I've chosen those fundamental problems. Have I correctly chosen the most important ones? Well, who knows? But it's my take, and I think it'll serve you well. So we'll have at it in a minute. What else do I want to say? Oh, I noticed that some of the worksheets are still in the room. That's too bad, because I always ask you to take those home and look them over. That's the case every class. So I hope I remember to talk to you about that tomorrow. This is muscle memory for me. Saying it now will help me remember perhaps to say it again tomorrow. Okay, so let's have at it. And the problems you're going to do are almost identical to the ones I'm doing for you here. But this is also a bit of a lecture. And I hope you take it all in, maybe in different stages. And I want to make sure I'm covered there that I want to cover. All right, so I'm just going to do some math now. So we're going to talk about the sine function, which is really about the heights in the unit circle. And when we are at 0 radius lengths or 0 degrees, we're at this location. That location on the circle. And we can see there's no height there, right? We have positive height above that, negative below. We're right in the middle. And then as we move around the circle, 30 degrees, a half, we move a little bit further up, 45 degrees, root 2 over 2, 0.71. And I'll be handing out a memorization sheet tomorrow. But you should know that already. I know a lot of you don't, but you should. Root 3 over 2, 0.87, that's 60 degrees. And straight up at 90 degrees is 1. And I showed you the first quadrantal relationships of angles to ratios. And the max is 1 halfway up, 30 degrees, that one. None of that should be new for you, but still might be worth talking about and repeating so that it's really part of your understanding. Now, the cosine function, when the heights are going up, widths are going down. And why? Because of this triangle, right? Height, width, Pythagorean relationship. We square that. We square that. It's got to add up to 1. Okay, and I think we can see that when we're at this location on the unit circle. No radius lengths. We haven't traveled any radius lengths. we're at a maximum of 1 squared plus 0 squared. I hope you can see. Yeah, barely. I'll put it back this way a little bit. Have to keep adjusting that. But 0 squared is 0, 1 squared is 1, sine squared plus cosine squared equals 1. When we have a 45-degree triangle, we got root 2 over 2, root 2 over 2. What do you get when you square root 2 over 2? You get 2 over 4, which is a half. And if that's a half and that's a half, that adds up to 1. And if you had root 3 over 2, and its counterpart 1/2, when you square that, you get 3/4. When you square that, you get 1/4. That adds up to 1. So sine squared of an angle, doesn't matter what the angle is. Sine squared plus cosine squared equals 1. That's an identity. That's the most important identity. It's used for many proofs at the next level, which makes me think I should do a couple of simple proofs with you. We'll see how it goes. I mean, you got to put the brakes on at some point. That's why I'm getting it fixed tomorrow or Thursday, because you got to have time to integrate the material. So how much can I put in front of you? Not going to put any more in front of you till I see how it goes and see how our learning rate is. And right now, we actually have enough material in front of us to have a good semester's worth of study. But if you can handle more, it'd be better for you. All right, so 30 degrees, right? As we go up and start drawing triangles, we can see that the width is getting smaller. As we go up and drawing triangles, we can see that the width is getting smaller. And over here, the heights are getting bigger. Can't see that one this time. Over here, heights getting bigger. Over here, width's getting smaller. Harder to graph the cosine, I think, because the y-axis, which is vertical, y-axis is vertical, but on the y-axis, you're actually listing widths. I think that poses a little problem for the brain, more so than heights to heights. All right, so where are we at? Where are we going with this? Well, the new topic. A couple of new topics. Cosine and tangent. Most important are the sine and cosine graphs. Tangent, if we can get to it a little bit, that's great. I'm going to look at it right now. Tangent is the heights divided by the widths. You have had to do a few tangents, a 3 pi over 4, tangent of 3 pi over 2. All right, so you got to get a little familiarity with some of those values. And the way to get tangent values really is to draw the triangles twice the size of the unit circle triangles. So make the hypotenuse 2, then you're not working with fractions. So just double the size. You know, if I had I want to mimic the 30-degree triangle. So good drawings get good answers. So let's see. Halfway. That's pretty good. Okay, if that's 1, then that's a half, right? But if you double the size, you get the same ratios. 30 degrees opposite to hypotenuse is the same as opposite to hypotenuse there. So you want to get in the habit of knowing your 30 degree, your 45 degree, and your 60 degree triangles. And straight up at 90 degrees, there's no width. You know, when you draw the radius straight up, can't draw the triangle. It's got height. The height's the same as the hypotenuse. The heights are the same, but the widths, no widths. And if you were to plot these values, the ones that are most important are 90 degrees and 90 degrees. I don't know if I've done one here. 90 degrees straight up, no width, height, and tangent is height divided by width. So this height divided by that width is 1 divided by 0. We've been talking about that as being undefined, and that's why you get asymptotic behavior at 90. The most important one, of course, is 45 degrees, and every chunk of 45 is, a certain number of pi over 4s. Anytime you see that, your answer is going to be plus or minus 1, depending upon the quadrant. In the first quadrant at 45 degrees, you got the root 2 over 2 divided by root 2 over 2, which is 1. And no height, so you get a propeller-shaped graph, and the fundamental period is 180 degrees, positive 90, negative 90 degrees to positive 90. All of the all of the ratios occur, and then they just keep repeating and repeating and repeating that pattern forever. How much are we going to do with the tangent function? Again, I don't know. Depends upon your learning rate. But I'm going to use the tangent function because tomorrow and Friday, you'll be solving sine and cosine functions. So I thought I would just do a kind of a basic trigonometric equation. This is a quadratic trigonometric equation. And so I only see the variable x in one position. So I know, just like the quadratics you've been solving like this, I can use inverse operations. So what would I do here? I would subtract 1, 3 tangent squared x equals 1. I got to shut the door here, starting to get some noise. Not sure what's going on. Okay. Then what would I do? I would divide by 3. So tan squared x equals 1 over 3. And then I would take the inverse of squaring. Tangent of x equals plus or minus 1 over root 3, right? Square root of 1 is 1. Well, that's one of our famous triangles. Root 3 is approximately 1.73. 1 divided by 1.73 is, well, we know it's bigger. It's less than 1, but it's bigger than a half. It's less than a half. What is it? It's bigger than 1. All right. So 1 over root 3 is 1. Root 3 is 1.73, so that should be drawn longer, I think. Let's see, I think I want to draw something like 1 over root 3. And we can see that's a 30-degree angle, right? Because if we were to divide by 2, you've got your 1/1/2 root 3 over 2. That should be a familiar triangle to you at this stage. So I now know that in the unit circle, that's what I'm writing here, 0 to 2 pi. I'll probably change that from 0 to 360 degrees for a while for you. I don't know why this is so difficult for folks to grasp, but all we're doing is finding what, well, I probably should have started with that. The question is, what are you looking for here? What does X stand for? And remember, you can pause this video anytime. You can replay. I'm just talking fast because I don't want to live here doing this. I got other places to go and things to do. But I want to make these videos to help you. I just don't want to have to spend a long time doing it. Yeah, but I'm happy to do it. Don't get me wrong. I want you to learn. Okay, but I'm talking fast. You push the space bar, replay anything I say. You got the technological skills to do that. All right, so back to what's it stand for? Angle. Okay. Remember, in trig, I give you an angle, you give me a ratio. I give you a ratio, you give me an angle. What are you looking at over here? A ratio. So therefore, what am I looking for? An angle. And I just found it. It's 30 degrees. But there's lots of other places in the unit circle where I get that ratio. I get it over here, I get it over here, and I get it here. All the 30-degree situations. Because over here, I get -1, minus root 3. And that's also positive 1 over root 3. Over here, I get positive 1, negative root 3. I already wrote the negative. And that's 1 over negative root 3. We move that into the numerator. And so what do we have here? We got 30 degrees, 150, 210, 30 more than 180, 30 less than 360. So this actually had 4 answers in this window. I'll call it a window. It's actually a domain restriction. 30 degrees, 150 degrees, 210 degrees, and 330 degrees. That's what you would list. You might want to start checking your answers a little bit now. So let's actually put one of those in here, and I'll erase the rest of this work. Let's put 330 degrees in there. All right, so how would we do that? Well, the order of operations here is really important. And we've talked about what you do first. In math, you do what's hardest. Historically, what do you think? You think we did subtraction, squaring, multiplication, or the tangent function historically last? I'm putting my money on the tan at 330. So we draw a circle, 330 degrees. We go over here, we look at that, and so that's -1. That's root 3. Yeah. And we think that's gonna work, so we put in that. So -1/√3 is what the tangent becomes. -1/√3, and then I'm gonna square it. If I square it, I get 3 times 1/3. Right, squaring the square root gives you what's inside, squaring -1, and then I'm subtracting 1, I can see the 3's cancel, and 1 minus 1 is 0. And so how do you solve sine, cosine, tangent functions when you only see one variable? Inverse operations. It's gonna take you a while to do this. I've been doing this for years. That's why it seems so easy, because I got the muscle memory, I've thought through the concepts, I work with it all the time. You wanna get better, you gotta get the reps. And don't expect it to come easily until you do the reps, and then expect it to come really easily. Okay, so let's stick with your tests are mostly going to be on the sine and cosine, because if you can work with those, you can handle the next level of study. All right, so what do I see here? Another quadratic, except that tangent. Oh yeah, height over width. I wonder if I could just solve it thinking about height over width as some fraction. So I got some fraction squared minus some fraction equaling 0. Well, that's on your last test. That's on in every single test you've had this term. How do you solve something like that? You put it in multiplication form. F times F minus 1 equals 0. And again, we're going to be looking for 0 to 360. And the notation I'm giving you is closed circle to open circle, 0 to 360. So you don't have to repeat 360. It's the same answers as 0 degrees. All right, so F could equal 0. So when is height over width equal to 0? Well, we're trying to learn that fractions are equal to 0 when the numerator is equal to 0. So where are the heights 0? On the right and left side. So we can see that my angle X is either equal to 0 degrees or 180 from that part of this equation. And when is my fraction 1? When is height over width equal to 1? Well, that's when we have √2/2 equal. Divided by √2/2, I almost forgot to say sine over cosine. When does that equal 1? The 45 degrees, right? So we have 45 degrees, and we also have negative height over negative width. Well, that's also coming from 45 degrees, so there's 4 of them. There's one there, there's one there, there's one there, there's one there. Radians are easier to work with. If you can say your answers in radians, it's quicker. So you got pi over 4, that's 3 pi over 4, that's 5 pi over 4, and that's 7 pi over 4. Right. Otherwise, you got to do 45 minus 360, which is 315, I believe. But I'm more used to working with that. All right, so tomorrow, you're watching this probably Wednesday night, probably tomorrow night. When you come into class, you're going to have 2 equations to work with. Probably sine and cosine equations. One you'll solve with inverse operations, and the other you'll solve with products, right? You're just trying to learn a language, so I'm happy to tell you how to do it. All right, so I want you to become familiar with the user-friendly arc sine values. Again, pause the video. You can try it. It's Wednesday night, you try it. But what you're supposed to get is a drawing. These are the angles, and these are the ratios in this case, right? So we want to go from ratio to angle. All right, now I'm looking at the heights. Well, what are the famous height ratios? Well, they are 1/2. So over here, if I drew the triangle, the ratio would be 1/2. And I hope you would see that it comes from a 30-degree angle. Whereas 45 degrees is √2/2, and that comes from the 45 degree. And then the one up here, remember the heights are getting bigger, right? Heights are getting bigger. Sine curve, heights getting bigger in the first 90. But we are reversing the x's and the y's with this. It's the inverse. So 60 degrees gets us √3/2, and 90 degrees gets us 1. Now, where students have trouble is that. And this is not the first time you've heard this, so I hope half of you right now know what that angle is. And that's minus 30 degrees. Oh, I forgot to put 0, get you 0, right? But that's the ratio, that's the angle. Or if it's in degrees, I should be putting a degree symbol there, otherwise it would have been radius lengths. So minus 30 gets us minus 1/2. I think you can anticipate this now. Minus 45 gets you minus √2/2. I want you to memorize what that is. You heard it once before. As a decimal, what's minus √2/2? Negative 0.71. Minus 60 degrees gets us negative √3/2. What's negative √3/2? Minus 0.87. And then minus 90 degrees gets us negative 1. Degrees, ratio, excuse me. See how dyslexic that is? I just did it backwards, didn't I? Look at that, dyslexic. Okay, what I meant to say here, because I wasn't thinking, I was lecturing you on behavior. So this should have been minus 1/2 gets us negative 30 degrees. Minus √2/2 gets us negative 45 degrees. Minus √3/2 gets us minus 60 degrees. And minus 1 gets us minus 90 degrees. Lost my focus there, got it back. All right, so you're going to be learning how to do that, I hope. Arc cosine of 0.02. I forgot to write this down. I wanted you to know that in Google, that's all you have to do. And if you want to put in degrees, you get an answer. Did I do this one? I think I might have. I think the answer was something like 14 point, couple of decimal places. I'm going to make up some right now, and it goes on. But all you got to do is type it in this, that first, what do they call it? Entry spot for search engine, whatever. You guys know. And it's a great thing. I don't know if you've heard of Google, but you put things in and you can find out lots of information. I typed that in. That's what came out. Of course, it gave it to me in radians first. But what are you looking at? You're looking at a drawing for me. And then you're going to anticipate on Thursday what I asked. Let's see how you do with estimating. And then actually use Google, find the right answer so you can start to see how it's right at your fingertips. So you got a circle. The arc cosine is the top half of the circle. This is a radius length now. No, it's not. It's a place on the ruler. Okay. It's almost identical to the radius length. Now, my calculus was coming in here. So there's a half, right? There's √2/2. There's √3/2. √3/2 is 0.87. Oh, I did. God, the one I did was close to, which one did I do that was 14 degrees? I think I did 0.97 earlier, right? Because as I'm looking at this now and not just trying to get through this too quickly, that was the one that was close to 14 point something degrees. All right, 0.02, where is 0.02? On this ruler, 0.02 is near 0, right? It's right about there. So we're looking at a triangle. It's hard to draw. Let me go up. Let's go there. And we're looking for that width. All right, now, how many degrees did it take to get that width? Well, you got to be pretty darn close to 90. Right, so this answer, which you can put in a calculator, just pause the video, go to Google, and I'm guessing this critter here would be about, I would do better with radians. This is probably around 1.55 radius lengths, but in degrees, I'm guessing it's pretty close to, I'm just going to say 0.99. What am I saying? 90 degrees is there. 0.89 maybe? 895? I don't know. Degrees. All right. It's 89.5 degrees. Whoo! Yeah. Catch my breath. That's what I'm getting fixed. All right. Yeah, final. But I'm not going to do this video again, despite the fact that it's going to be publicized, because I don't know how to upload these things using Canvas without having to sit there for a half an hour. Whereas YouTube does it in 3 or 4 minutes. So I'm going YouTube. All right. So let me try to do another one here just to give it some justice, and I will really give some thought to it. So let's look at the arc cosine of, how about negative 0.6? Negative 0.6. Okay, so how do we do that? Well, you got to be on the ruler first. All right, because negative 0.6 is really negative 6/10. So it is a ratio. And we're going to look for the angle. Okay, and this is pretty close to minus 5/10. And I know what minus 1/2 is. That's 120 degrees to get to minus 1/2. So my answer should be a little bit further. So I'm going to guess 100. I might have said minus angle. 120 degrees gets me there, right? So I'm going to guess maybe 124 degrees might get me there. But that's a wild guess. Yeah, go put it in Google, see how close it is. I had to have to give it more thought about how it's not a linear situation, right? Movement on the arc. So you'd have to really do some estimating. Boom. There's the 1/2. There's the minus 5/10 for the width. I'm going a little bit further, 1/5 of the way to here. How much did it change to get to here? How much angular change from 120? I don't know. I'm just going to say that. All right, so that's what we're going to practice. And the more we practice, we're all going to get better. I'm going to practice right along with you, giving it some thought. All righty, so that's a topic that we're going to work with. And the other one is, now where are we going? Oh, I might be out of order here, but let's look at the arc cosine of, let's do the sine of the arc cosine of minus 5/9. This is not new, okay? But when you don't have one of the famous ratios, or if you're not just trying to find the angle that creates that, you're doing more work, then you just want to draw it in terms of adjacent to hypotenuse, which in this case might be, let's shorten that so I have some room here. There, that's not too bad, minus 5 to 9. So 81/25, 16/5, 56. That's that square area, so that's the square root of 56, which is 4 times 16, I think, 16, not 4 times 14. 4 times 14, so this is 2 root 14. I don't care if you say that. Your answer here can be square root of 56/9, because that tells them you understand that concept. All right, what I just did was the square root of 4 times the square root of 14/9. I called it 2 root 14/9 would be the side. I don't know if anybody's going to make you do that or not. I'm not going to make you do that. All right, so where are we at now? We're at moving right along. This is the 20% more problems that we're going to cover during the second half. 80% we've already covered of what I'm expecting us to learn. But again, whether or not I tack on a problem or two depends upon what I see in class. But the brakes are on. Well, mine aren't yet. They got to get fixed Thursday. I told you that. But they will be on. All right, so how do we graph y equals c to the x? Not the first time you've seen that, but the handout's going to give you some memorization. So you're really looking at 2.71 to the x, which is less than 3 to the x, but greater than 2 to the x in terms of a base. All right, so that base is somewhere in between these two graphs. So if we graph those two, this one is always in between those two. What are the ones that I want you to know? I want you to know e to the negative 1.1, e to the 0.7, negative 0.7, e to the 0, e to the 0.7, and e to the 1.1. We're going to be working with those significantly. I'll just talk about this one right now because I think it's the one we want to use, that one and this one, in order to graph 2 points in an asymptote. Asymptote is 0. And over here, when we have negative exponents, that's 1 over e to the 1.1. And as this number gets bigger, the fraction keeps getting smaller and smaller and smaller. And so this is basically the shape of an exponential growth function, which is what these are. And where did I get these numbers? Right off a calculator. Okay, so if we want to do e to the x equals 3, how would we find that? Well, we would have to do log base 2.71 to get 3. We go to a calculator, we go to a computer. Right? But of course, this function is so important, it gets its own notation system. Now, everybody knows pi, you know, your brain goes 3.14. Well, I want your brain to know E goes to 2.71. And this goes on forever the same way that does. And maybe we'll, in class, talk about where the number comes from, at least from a limit standpoint. But you don't need to know that immediately. Immediately, you want to get these numbers memorized as quickly as possible. Because once you have those numbers memorized, you can start to work with this function. All right, so all we need is 2 points. And what I'm going to do is standardize this. Whatever that height is from the asymptote, we're going to learn to triple it. And we're going to get a good graph by picking what numbers? 1.1 and 0. Okay, and I've uploaded a video with more challenging graphs. But you can get this graph down 10 seconds or less. Okay? A couple of weeks from now, some of you will be able to graph this in 10 seconds or less. So let's look at this again. 2.71. Mathematicians don't work with 2.7 we just say E. And we don't say log base E because this is so important. We keep the L, which means log. I'll put a L that way for now. L, but you will see it this way, L, N, the natural log, because this rate of change happens in nature a lot. You're going to use E in money and banking if you go into the financial sector. You're going to use it in your science classes. You're going to use it in any kind of physics work you're going to do. You're going to work with it a lot. So it's a good time to get familiar with it. So the ln of 3, if you type it in your calculator, it comes out as approximately 1.1. So if I wanted to write 3 to the x, it's approximately equal to e to the 1.1x. Now you're hearing a lot of new stuff today, just like the other stuff you've been working on. It takes time. And the reason I'm doing it this way is I've never had anybody come into my class that could graph the ln function, tell me what a logarithm was, work with the rules of logarithms, or solve a logarithmic equation. Okay, so I know this takes time, and the only way for you to learn it is for me to present it early and you to have a long time to work with it. And that's what we're doing right now. Okay, so this is an initial explanation, you're just trying to follow. So how would I graph this? Let's go and actually graph the one. Let me get everything else out of the way. You can always replay any part of this. So what do I see? I see e to the positive x, which means it's growth. If it was e to the negative x, then the picture changes to decay. But right now I'm looking at growth. So that means I can come in with the asymptote, the general shape, and the constant. We've been graphing some exponential functions, so that's not new. The only thing I have to do is find 2 places on here, and I know what e to the 0 is. It's 1, and I now know what e to the 1.1 is. We're going to call it 3. Probably closer to 2.989, something like that. We're just going to call it 3 because we want to get a feel for this. So what does that tell me? That tells me that I want that and I want that. So if I let x equal 0, e to the 0 is 1, I'm 12 units above -5. So therefore 0 gets me what, 7? Now, if I let this become 1.1, well, e to the 1 is 3. I get 3 times this. Yeah, I'm hoping that looks to be about 3 times that. That's 36 units. When does that happen? At 1.1. 36, take away 5 is 31. You're done. And you have a feeling for other values. Now, what's another value that maybe shows up here? Well, 1/3 of 12 is 4, so -1 over here. Let me see if I can get this so that I can. So -1 will happen when I pick an x value of negative 1.1. If e to the 1.1 is 3, then e to the negative 1.1 is 1/3. And 1/3 of 12 is 4, and 4 minus 5 is negative 1. Now, you don't need a third point. I'm just giving it to you so that you can see that really things are growing if I look into the future from this vantage point, decaying if I look in that direction, getting small. All right, so that's how we're going to practice graphing e to the x functions. We're going to do it Thursday, we're going to do it Friday, and then it's going to be about 75, 80 question worksheets for the rest of the semester. And you start chomping away at the ones you don't know how to do. Maybe I'll just construct them backwards. That's what I'll do from now on. I'll put the newer material first to make sure you get to it, and how to write the equation of a line, stuff like that at the end. Now, I'm going to graph LN functions. And it's really dyslexia that gets in the way of right answers. All right, because now, instead of going from 1.1 to 3, we're going to go from 3 to 1.1. And I think we looked at, and we'll look at in class, the paper change, right? X's to y, y's to x's. So a horizontal asymptote for exponential functions become vertical asymptotes for logarithmic functions. So what do we know? We know that e to the 1.1 is equal to 3, and we know that 1.1 approximately. It should be saying something that's true. And 1.1 is approximately the log base 3, the log of 3, the ln of 3. Woo! Tired. Okay, so the ln of 3 comes off a calculator, 1.1, and I hope everybody can get a feel for 2.71 to the 1. We know it's 2.71. If you went a little bigger, you should be a little bit bigger than 2.71. I think 3 is. Okay, so what do we do with logarithm? Let's cut to the chase. Whatever the parentheses is, whatever is in there, set it to 0, set it to 1, set it to 3, and know that logarithms that we're going to graph have either that shape or this shape. I could do reflections, but not necessary for you at this stage. So what makes a 0? 0. Right? Because if this is the inverse of growth and decay, where time gets you a quantity, right? Then this is the inverse of that. So we're doing quantity. I'm going to use quantity here back to time. That's basically how we'll be talking about them in class. All right? Quantities back to time. Quantities of what? Radioactivity. Quantities of money in a bank, savings account, loans, things like that. Okay, which change exponentially. Okay? Well, we can't talk about the time at which a cornfield is a certain height unless there's something there. So if there's nothing here, you can't talk about this calculation in any physical sense. So therefore, your quantities have to be bigger than 0. This parentheses has to be bigger than 0. Well, right now it's x. So x equals 0 means that only numbers bigger than 0 will show up on the graph for x's. They gotta be bigger, they gotta be positive. So what are the numbers that are easiest? 1. Right, that's asking the question, what do you put on top of e to get 1? Everybody knows that by now. I hope it's 0. And 0 times anything is 0, you always get that. So it's, when you make that a 1, you're going to get that. So in this case, 1 gets us 9. Okay, what's the other one that I'm hoping becomes familiar? Maybe you already know the ln of 3. 1.1 times 2, 2.2 plus 9, 11.2. And that happens when x is 3. Here's your graph. And now, you might want to say -3, but no, you can't. You can't, no. But you could have said 1/3. Because what's the exponent you put on top of e to get 1/3? negative 1.1. Negative 1.1 times 2 is negative 2.2. If you take 2 away from 9, you got 7, so 6.8. So 1/3 gets us 6.8-ish. Pretty darn close. Now, could I keep doing that to 1/4, 1/5, 1/6, so on and so forth? Absolutely. And will we be looking at what exponent puts us on top of, what's the ln of 9, for instance? Well, that's asking the question, e to the what equals 9? Well, I know what 9 is. 9's 3 squared. And I know what 3 is, e to the 1.1 squared. Oh, I now know that 2.2, roughly, gets me 9. We're going to be doing some of that work in class. Again, it's going to take time. Whew! Yes, what do we got here? A sinusoid. Can I graph sinusoids? One period. All I'm looking for is one period. Okay, and the more you get familiar with the values we started off talking about at the beginning of this video, which is getting rather lengthy. All right. Sine function, one period, looks like that. Cosine function, one period, looks like that. You got to get familiar with that. All right, this is heights, right? And at 0 degrees, there's no height. And at 90 degrees, there's the maximum height. And then at 360, we come back to no height. Widths would be cosine. What's the width at 0 degrees? A max. And then 360 degrees, we come back to that max. All right, so how do you solve this? How do you graph this? You graph this by doing sine function. Okay, you can think of it as a mountain valley shape. Got a middle, y equals 10. The normal sine function goes up and down 1. That's all you get out of this is numbers between 1 and negative 1. You're quadrupling them, so therefore you're going up 4 and down 4. So therefore I know that this y value is 10, and then this y value is, and you should do this. Let me do this again. So best way to graph these is to set up some forms. All right, pour the concrete in. All right, and then bumpity bumpity. Oops, went too far. Okay, and label that as height of 14, down 4, 6, middle 10. Okay, and this is called the amplitude. That's the amplitude, which is always positive. This is the average value. And so we're going up and down 4. And we start at 0, and we can see that that's 10. And we come over here, and we see that that's 2 pi once around the circle. 6.28 units later, we're back to 10, and we've taken 1 trip around the circle, and that's the graph. If that's 2 pi, it's so easy to call that pi. Call that pi over 2, get you 14, pi gets you 10, 3 pi over 2. Those should start to sound familiar to you at 90 degrees, 180, 270, hopefully so. All right, and I've got rapid fire 5 videos for you anytime you want to practice any of these skills. Almost done, I think. A couple more problems, and that's the 20% increase in problems that you're going to be working on. And you want to get enough reps in so that you can do them easily. And that's like working your left-handed layups and your left-footed push passes. You got to put the time in. All right, so how do you solve something like this? Because the video is getting so long, we'll talk about graphical. It's quicker to do it graphically. But what you want to do is you want to do a sign chart. And you put down the critical numbers. 0 is critical. 4 is critical. And -5 is critical. I hope you noticed that I put dashes and a dot. There's reasons for that. And all you have to do is pick a number bigger than the biggest root. So let's put a number like 7 in. All right, if I put a number like 7 in, 2 times 7 is 14, which is a positive number. 7 minus 4 squared is a positive number. And 7 plus 5 cubed is a positive number. And is a positive times a positive less than 0? Heck no. Or you put false. I know that's going to be false. Doesn't matter because that's an even integer. That's an even exponent. So I'll pick a number less than 4. 3. Put a 3 in. 3 minus 4 is -1. I get a sign change here, but when I square it, it's still positive. All right, so that's a positive multiplier. 3 times 2 is 6. That's still a positive multiplier. No change there. 3 plus 5 cubed, no change there. Still less than 0. No, I knew that without having to do this work. And with practice, you'll know that too. At 0, which is really to the first power, you know, y equals x is a linear function. 2x is a linear function, which changes from negative to positive. Right? X squared doesn't change, right? Positive y's, and the cubic changes. So hopefully you're starting to already see that whether it's odd or even dictates these. But let's put a number between 3 and 0. Right? So we checked. We used 3 as a check. We use 7 as a check. Let's use, oh, we already, where am I at? I'm losing my train of thought. Okay, so that's still 0, right? Yeah, so we've already done that one, really. We put 3 in, so we know that's false. So let's pick a number here, -2. Just pick -2. All right, so -2. Well, what's -2 times 2? It's not positive anymore. There's a sign change. You said odd would have a sign change. Whereas -2 minus 4, -6 squared, that's always positive. There's no sign change coming from that column. And -2 plus 5 cubed is still a positive. Right? And a negative times a positive times a positive. You know what? That is less than 0. That's true. Now we're going to put a T there. I know this is going to be false, so automatically, because there's going to be another sign change. And so let's pick a number to the left of -5. I like -1,000,000. I prefer those than actually these numbers. Although I only need to look at this one, and then the rest is 5 seconds with practice. So -1,000,000, big negative number. Well, that's still negative, nothing affecting that. Minus a minus squared, well, that's always positive. That's always positive. But what happens over here when I put -1,000,000 in? Oh, it stays negative, and a negative cubed is a negative. I get a sign change. And if a sign change in a product means what used to be less than is now greater than. And our original was it has to be less than. So false. This is greater than that. So false to that original equation. Knew that to begin with. So there's only one interval that works, and that's x's that are less than 0 but greater than -5. Now, if I put an equal here, then we got to put equals there. And if you wanted to use interval notation, -5 to 0, you could say it that way, but if it's usually just one interval, that causes less confusion. All right, one last problem, and then I'll give you some time off. I don't know if I'll give you time off for having to watch this long video, because you're supposed to get an hour of homework every night. Usually I teach without much homework, other than study your answer key on the test. And on a nightly basis, I try to give you that opportunity. But since it's new material, I suppose an hour here isn't so bad. So what do we got? The last problem. And if you practice these enough, 2 weeks from now, you can write your answer down no matter how I change these numbers. This one would be x squared minus 6x, 9 and 16 plus 25 equals 0. Just looking at it. All right, there's a way to get that answer, but you should practice what's going on first. So how do we get from here back to there? You pause the video and think about it a little bit if you want. Just going to show you. Well, first off, this stuff has to move because I've got 0 on the right. So how do I move a 3? X minus 3 plus or minus 4i. Okay, when do you get answers, imaginary answers? When you take square roots of negatives. So this really came from, and I don't think you need to show this line of work too often, but this really came from plus or minus the square root of 16i. If you're paying attention to the other work, you should understand that. Now, how do I get rid of square roots? I square things. We've been practiced binomial squaring. I shouldn't have to put it in parentheses and put a square. You should know that's x squared minus 6x plus 9. And if you square this, squaring plus or minus is always going to be positive. Squaring the square root of 16 is 16, and squaring I is I squared. That's negative 16, yes? And so if I bring the negative 16 over, I get x squared minus 6x plus 25 equals 0. Practice those. Now that's a whole lot easier than the textbook method, which I don't even like to write, which is x minus 3 times positive 4i times x minus 3 minus 4i. Kind of like a conjugate. That's textbook method. You got to multiply that out. I think it's much easier just to understand this process and write your answer. Now that's going to take you practice. Every single one of these problems is going to take you practice. Did I cover everything? No. There's more. Yes. And the easiest one last. All right, so let's see. Boy, oh boy, oh boy. Now, I was going to come in tomorrow morning at 4 in the morning to do this, but I decided that I didn't know how long it was going to take me because I got to do it for another class. And I got to write 2 worksheets up for you to keep you busy. So let's look at absolute value. And let's talk about writing this as a piecewise function. I've got smudges. So, not the first time you've heard this, y equals x. That's this graph, which has negative y values to positive. What happens when we slap an absolute value on it? The negatives become positives, and you get a reflection. And this is going up at 1 to 1, and on this side, we're going down at 1 to 1 because you follow from left to right. So what is this as a piecewise function? Well, as a piecewise function, I could have written it as Alfred Hitchcock. Negative x when x's are less than 0, positive x when x's are greater than 0. This is the y equals x side, and this is 0. When I'm bigger than 0, I get y equals x. Over here on the other side, I get y equals minus x. All right, so what are we paying attention to? 0. I guess if we're going to find the vertex of an absolute value, we want to create 0 inside the absolute value right? Symbol. All right, so how do I write the following as a piecewise? Y equals, let's do 4, absolute value of, let's do a more complicated one. Let's do 3x minus 6 plus 7. Do I want to do that one? Sure. So y equals Alfred Hitchcock. Well, I know I got a V-shape. Oops, there's one of those worksheets somebody should have taken home with them. I know I have a vertex at 2, 7. And I also know that this is going up at 12 to 1, and this is going down at 12 to 1. How do I know that? Because all you have to do is the left side is, I know there's an arrow here. All that means is you go into infinity. We're really looking at coming down in this direction and going up in that direction. So, rate of change is really both multipliers here. But all you have to do is write minus 4 times 3x minus 6 plus 7, which passes through 2, 7. And it has a decreasing slope of 12 on this side. And on this side, it's just positive 4, 3x minus 6 plus 7. But where is the hinge? At 2. Numbers bigger than 2 for x put me on the increasing side. Numbers less than 2 put me on the decreasing side. And so this is only true for x is less than 2. This is only true for x is greater than or equal to 2. And it doesn't matter whether you put the equal sign here or here, just include it with one of the branches. Okay, so why is that helpful? All right, why is that helpful? Because if I solve an equation like the following, let's do 5 times x minus 7 plus 2, and I want that to equal 17, say. Well, it's a no-brainer. Just write the 2 parts. Minus 5, x minus 7 plus 2, and also, or, I'm going to use or and right now, 5, x minus 7 plus 2, equals 17. You see all that? Yes. So, just do it here. So what are we gonna do? Subtract 2, 15. So you don't have to do any thinking here. 15 divided by -5, -3. So that's gone, that's gone. Add 7, and you got 4. There are a few shortcuts to even this, believe it or not. Over here, you're gonna subtract 2, 15, you're gonna divide by 5, there's your 3, you're gonna add 7, 10. Doesn't hurt to check your answers. 4 minus 7, -3, that's a value, -3, 3 times 5, 15, plus 2, 17. At this stage, how far is it from the vertex? 7 to 10, 3 units, which means this has to be 3 units back. You can add 14, 4 and 10 get 14, divide by 2. If that doesn't take you to the middle value for X, then you made a mistake. And then inequalities, what if we change this to greater than 17? Well, you can do the same thing you did in the last problem. Find your answers, which we just found were 10 and 4, I believe. It breaks it up into 5 possible answers, interval A, interval B, interval C. 10 could work, 4 could work. And then we just check and find out what does work and what doesn't. I'll pick a number bigger than 10. I'll put 1,000,000 in here. 1,000,000, yeah, times 5 plus 2 greater than 17. That's true. You'll find that these alternate. But let's put a number in between 4 and 10, 7. 7, does 7 work? 0 times 5, 0 plus 2 is 2 greater than 17. No, it's false. And then put minus 1,000,000 in. Well, minus 1,000,000 acts exactly the same way as positive 1,000,000 does, right? Because the sign is going to change. 5 times 1,000,000 plus 2 is certainly greater than. So how do we actually write this answer? Let's see. Oh, I had 2 more things I wanted to show you, really quick and easy problems, but this is getting way too long. So how do you write this answer? Negative infinity to 4. This is where interval notation also 10 to infinity. I'm going to stop it there because I'm starting to lose my mind too. All right. I think I lost my mind a long time ago. All right. So I'm going to upload this. And while it's uploading and going on to the old YouTube channel, I'm going to keep busy with something else here. So I don't have to come in tomorrow so early. All right. See you soon.